Shall we get started? Is everything hooked up? Okay, let's get started. So I have a couple of announcements, and then we'll hopefully talk about the questions you have on projects as well as lectures. The first thing is my office hours today are pushed to 7 to 8 p.m. There's a talk by Google, Alfred Spector, I think head of Google's research, at 4:30 p.m. in the CS department in the Rashid Auditorium. So if you're interested in attending, you can look it up also. I don't have the email right now, but maybe if my TAs remind me later on, we can send an email about that. That's a note for you. That clashes with my office hours, so I'd like to attend that. But you can come and see me after 7 p.m. Is that good? And you can always come and see me by making an appointment. You can try whether I'm here or not. I'm usually here, so that could be a good bet too, especially late at night. One of the things we will have to revise is the exam date. Currently, it's scheduled on October 18th, but a couple of you told me that October 18th is the mid-semester break. Do you guys care? Some of you care. Okay, that means that we'll need to reschedule. So we'll get back to you on this. It'll likely be the Wednesday of the following week, which is October 23rd. Okay, which means I will have more material to cover by the exam time. But I don't want to keep it on the mid-semester break. Okay, everybody happy with this?
You see the same time, like during the recitation time?
Yeah, so it'll likely be during the recitation time, yes. And we'll have to figure out how to do the online thing also. So there'll be honor code. Nobody talks to anybody else about the exam, right? That's important. You guys are graduate students. Actually, it doesn't matter. At Michigan, we used to have the honor code. We didn't even have proctors in the exam. Some exams, not all exams. The honor code is you're an honorable person. You just do your exam on your own. That's it. It's simple for me. Okay, calcium seminars. I discussed this before, but I'd encourage you to attend the calcium seminars. And do we have a link from the course website for this yet? I think we were going to add a link.
Yeah, we're going to add a page.
Okay, yeah, let's add that link. Until then, I think if you search for calcium CMU, you'll find these calcium seminars. And that's it basically. So we'll have a bunch of seminars related to computer architecture coming up. For example, one is next week, October 8th, a path to achieving sequential correctness for parallel programs. So it could be interesting for you. And later, Sima Setumadawan from Columbia University will talk about some security-related issues in computer architecture. Likely. The title is not there yet, but later, Yanjing Li will talk about self-repair of one core components in a robust system on chips. This is October 22nd. Actually, on October 21st, she will give a guest lecture in class. So our recitation is normally scheduled at 7:30 to 9:30 p.m. So we'll use that time for a guest lecture. So I hope you will attend that because it'll be interesting it'll be on a topic that I will not normally cover, which is resiliency techniques in computer architecture. How do you ensure more reliable design of computer architectures? So keep that, add that to your calendar. October 21st, we will have a Monday recitation on resilient computer architectures. So it'll be broader than this talk. And I'll give you an outline. I'll send you an outline of that guest lecture. So it should be interesting. And Yanjing does research. Her dissertation was on basically self-testing, online self-testing and self-repair of multi-core processors. So she has a lot of experience. She's right now at Intel. She did her PhD at Stanford. So this talk will be a much, much shorter version of the guest lecture. Guest lecture will cover a lot of issues and a lot of other works as well, done on resilient computer architectures. And later, October 28th, Wenmei Hu from Illinois will give a seminar. I don't know what it will be about yet. But Wenmei has worked on a lot of compilation techniques for superscalar and VLIW processors, like the impact compiler, the superblock scheduling, and hyperblock scheduling. A lot of those block-based optimizations have come out of his group. I don't think he'll talk about that. He's working on GPUs, GPU design today. So there'll likely be a talk on GPUs over here. On November 1st, Jing Li will talk about, I believe, the memory designs, new emerging memory technologies that she's been working on at IBM Research. And she's actually prototyped a lot of phase change memory and resistive memory chips. So I think she'll give a seminar about that. And later, we'll have another seminar on November 5th. So you'll see the wide variety of topics. Kushagra White from Microsoft will likely talk about data center design issues that are happening at Microsoft in his group. Basically, he's the head of the platforms group, hardware platforms group, and that looks at what kind of architectures should be used in Microsoft data centers to improve power efficiency, reliability, and performance. So I'm assuming he will talk about some of the challenges they're facing in that area. So this should be a pretty interesting set of talks that will complement nicely what you're learning in this class. So I would strongly encourage you to attend these. And some of the times are different, so you can get these times. The next week's seminar is in Hammerschlag Hall D level. If you don't know what HH stands for, we have an aliasing problem here. There's Hammerschlag Hall and Hamburg Hall. But this is Hammerschlag, not Hamburg. What is Hamburg normally referred to as? HBH? Oh, OK. Yeah. I see. I guess that's how the aliasing problem is solved. Yeah, adding more information.
We had a question from me here online.
Yes.
About whether these would be available to online student stall or recorded.
Yeah, so that's a good question online. I'm working on that, but these are not normally part of the course. So we'll try to make as much as possible available among these seminars. I am assuming you're interested in these, Mihir. That's why you're asking. So I'll try my best to get these recorded also. But these are not normally part of the course. Maybe Akatar can help us record some of these. I guess if we load Panopto, yeah, you can take a look at the schedule. And if we can work with the presenters early on such that Panopto is enabled on their computers, then there's no reason why we cannot record them, right? As long as they're OK with recording.
You could bring another Panopto-enabled computer and record them yourself.
Yeah, that's another possibility. OK. Yeah, so the guest lecture will be recorded. The guest lecture will be recorded and available. So I know that one because that's part of the course. That's October 21st, which is not here. But these will hopefully be recorded. OK? So try to attend these. And some of your readings may be some of these seminars at some point. We'll see. But even if they're not assigned as readings, I'd very much encourage you to attend these. And if you would like to get up-to-date information, basically you can subscribe over here. If you look at this, it says a mailing list keeps members informed of seminars and events related to calcium. Subscribe here using a cmu.edu or pit.edu suffix email address. OK, so that's upcoming calcium seminars. I guess I should add here 2.1, guest lecture on October 21st by Dr. Yanjing Li on resilient architecture design, or reliability techniques in architectures. OK? OK, any questions on this? OK, another announcement, feedback on paper reviews. We've been going through some of the paper reviews you've done so far as a batch of reviews. We're not going to provide you individual feedback in every single review, but we're going to give you feedback on overall trends in your reviews. Some of you hopefully received emails from the TAs. If you haven't received things, you will receive them. Basically, this will be general feedback on your reviews, how to improve them going forward. Okay, how many of you have received emails on this? OK, it's almost half and half. OK. So we'll have to finish this soon. OK, if you don't receive emails by the end of, I guess, this week, Friday, just send us an email, OK? But you should get them, unless we somehow missed it or it got lost in the email. Email is not a reliable medium, right? That's OK, so feedback on proposals. Have you all submitted proposals? I'm hoping, since you're coming to the discussions. OK, good. We've received how many? 27 proposals. I think I received 27 proposals. I don't know if that's about right or not. But online students or students who are watching this later on, if you haven't submitted your proposal, you should definitely contact us because the deadline is passed. And there should be a good reason why you haven't submitted your proposal. And I'm willing to talk about it. But I guess it doesn't apply to anyone who's here. OK, so you will receive feedback, and we'll try to prioritize this feedback. But in the meantime, if you want feedback, come and talk with us on ideas and to get feedback. So what we will do is we'll have a TA assigned to your proposal. And that TA will be basically your guide throughout the semester. And there will be a second TA also, who is the second guide. And you can talk to me about all of the proposals. I tend to give all of you feedback on all of the proposals. But you'll interact mostly with that TA for your project, OK? And yeah, basically keep engaged. This is very important. Project is the most important part of this course. So don't drop it. Keep going. So general feedback. I think I've looked over some of the proposals. I haven't gone into fine-grained feedback yet, but there were some proposals that didn't have a title. It's good to have a working title. You can fix that for the next time. Project proposal is not a good title. I cannot look at the proposal and say what this project is about, right? Yeah, think about this as so at the end of the semester, you would like to have a paper that's submittable to a top conference. That's the goal. It's a good bar to have, basically. So no paper starts with a project proposal. It's good to have a title. You'll change the title later on. That's fine. You'll adapt the title. You'll adapt everything. But have a good title that is descriptive, right? For example, if ACS was starting, I would start with accelerating critical sections, right? Something like that. Or identifying, if it was bottleneck identification and scheduling, identifying bottlenecks in multi-thread applications. If you're trying to figure out the critical path in a multi-thread program, and new critical path prediction mechanisms in multi-thread applications, something like that, right? Project proposal doesn't work. Write your name and affiliation. I know the template that we provided on the website actually didn't have the names because it's actually submission to a conference, but I do want to see your names for this class. It's important to have those names. And it's good to have it as part of a normal paper, right? I guess affiliation is good too, like your department. And I guess Carnegie Mellon University is a good one too. And follow the guidelines. This is important. I know some of you did not follow the guidelines. Your proposal should be, I guess, let's see, double column, single spaced, right? I received a lot of proposals that was not like that. It was not the majority, but it was a minority. But follow the guidelines in the next iteration, OK? And LaTeX was recommended, and there's a clear difference between a LaTeX proposal and a Word proposal. Like if you're doing research, I would definitely encourage you for LaTeX. Not because I have any profit that I will make from LaTeX. I don't know if anyone has any profit, makes any profit from LaTeX, but that's a lot more professional. Actually, LaTeX is used in typesetting a lot of books today. I don't know if any books use typesetting with Word. But I pity the people who are doing that typesetting well, if they do it. Yeah, try to use LaTeX, especially if you're going to publish papers in the end. But I'm not going to enforce that. But I'm going to enforce the guideline following because I'd like to, because it's very different to have a double column, single space paper versus single column double space paper, right? That's exactly the opposite, but the amount of things that you can say in that paper and the length of the paper is very different. So it's good to have that consistency. But LaTeX is strongly encouraged. Okay, any questions on this? These are general feedback. I'll give you specific feedback on your particular proposal. And watch out for that over email, or we'll schedule meetings. Okay? I think for now you can assume that you'll go ahead with your proposal, because I don't see any clear downsides, and many of you vetted. If you especially vetted your proposal with me and with the TAs, then keep going in your research. Basically start your literature survey, for example, figure out if anyone has done it. Start your evaluation infrastructure, for example. Start testing your ideas, basically. Feedback will be just another input. That may change your direction a little bit. Okay. Okay. Any questions on projects, proposals? Okay, good. Okay, so lectures. Are you guys following the lectures? Yes? What lecture are we on today? Okay, memory hierarchy. So I guess you have that. We're starting the memory hierarchy today. But what we have is actually, let's see, module schedule. So we covered a lot of speculation last week. So hopefully you've done all the readings and provided the paper reviews. Today's and Friday's online lectures are really brush up. So this is actually material that I would expect you to know by now, but I think it's good to synchronize everyone to be on the same page. So we have a lot of lectures on virtual memory, and it is a lot of lectures, I understand, but this is really a brush up, because this is really material that you're expected to know coming into this course. They're on virtual memory, and there are 3 lectures on virtual memory, one on memory hierarchy for today, caches, and advanced caches. And then after that, we'll move on to shared cache management. And all of these videos are up, so you can go ahead if you will. Some shared cache management techniques in multi-core processors and multi-threaded processors. And these are divided into small pieces so that you can, for example, if you pick one of these, I guess I shouldn't do that. No, I cannot get back. Yeah, I can. Let's see if this will work for me. No. Okay. You'll do better than I do, hopefully. Basically, you can watch it through Panopto. That has the slides also. And then we will go into main memory. And we have a bunch of lectures on main memory as well. After that, we'll cover emerging memory technologies and memory interference and quality of service and other approaches to quality of service. And then we'll start interconnects. So this is the first interconnect lecture, and then I'll continue adding more interconnect lectures over here. And after we finish interconnects, that'll be the end of the memory hierarchy. Does that make sense? Memory hierarchy is a very important component of modern systems, so we're going to cover a lot on memory hierarchy. We may even add more after this. So a lot of issues related to memory hierarchy, and I'd encourage you to read a lot as well. This is a great area to do research in. Okay. I guess any questions on lectures? Otherwise, I'll talk a little bit about memory hierarchy. Any questions on speculation? Oh, okay. I guess you've done the memory scaling write-up, right, earlier. You read a paper. So what we'll cover will relate a lot to that write-up that talks about like some of the challenges and solution directions in scaling memory hierarchy. Yes?
General speculation question. How does I/O usually handle the side effects of any kind? That, many times this is not mentioned at all when speculation is discussed.
That's right. So that's a great question, actually. I briefly mentioned that, I think, in transactional memory, in one of the transactional memory lectures. Oh, yeah, the question, yeah. Basically, the question is, how do we handle I/O in these speculative execution models? Or in general, side effects like things that would change the architectural state, right? I briefly mentioned that in the transactional memory lecture, I think, as one of the challenges in transactional memory. For example, if you do I/O in a transaction, how do you handle that? Because you're executing speculatively in a transaction, and you don't want to change the state of some other device that you're dealing with. So basically, the basic approach is similar to everything. If you're doing something speculatively, don't change any architectural state. That's the idea. Then the key question is, how do you do that? Without knowing that speculation will be successful, you should not change that architectural state. And you can only change the architectural state at the end of the speculative execution. Right? For example, with transactional memory, one approach could be, well, don't have I/O within a transaction, right? That could be one thing, and people have suggested that, right? Not having network I/O within a transaction, for example, but that is a challenge.
Does it throw exception if the user tries to?
Yeah, if the user adds I/O in their transaction, you do some analysis in the code and say, sorry, you cannot do this, right? Because how to handle it could be a problem, right? Do you actually execute that I/O operation? I mean, another very extreme approach is actually design the entire system to be speculative. Like your keyboard can speculatively give you, that's very hard to do. That's very, very hard to do, right? Your keyboard can give you speculative data and still preserve its state, knowing that this was a speculative request from a transaction. I mean, you can imagine something like that, right? If you have control over the entire system. But that's very tough to do in today's systems. So this is a problem. In general, the solution is either not having it, breaking the transactions in the middle of I/O. If it's a speculative execution model like dual core execution, for example, then it's easy, right? Because you just don't execute those operations. You can ignore those operations. You can make the result registers invalid, for example. Those are easy operations. Transactional memory, it's much harder. Because you really want to do this I/O operation in a transaction, for example, then it may not work. You may need to resort to locks, for example. You can delay the I/O operations, but then again, if you have side effects, that's tough, right? If you're going to use that information coming out of the input device, then that doesn't work. If you're writing to an I/O device, then you usually can buffer those operations. So writes are a little bit easier to handle than reads. So you can write to the I/O device at the very end of the transaction. Now this doesn't work, of course, if you're going to read from that I/O device later on within the same transaction, right? So you got to preserve those dependencies. But that's a very good question. This is a general problem with transactional memory. Yes?
This was somewhat prompted of the multiscalar paper. I don't think they talk about it. So why do they get away to not even mention it?
So that's a good question. With the multiscalar paper, I think it's a little bit easier to handle also, because what you can do is basically, in that case, that I/O operation could be a task by itself, for example, right? Right. With transactional memory, it's harder, right? Yeah. So if you make I/O operation task by itself in multiscalar, it should work. Or basically end the task at an I/O operation. Maybe they don't talk about it. Maybe in later papers they talk about it, but they may not have talked about it in the earlier papers. So anytime you can break the task at an I/O operation, this should work, or the side effect, it should work. Yes?
There's an online question about
Sure.
how to debug programs in speculative models and on multiscalar processors. How do you do debugging when code sections are executing simultaneously?
Oh, I see. That's a good question. Good, you guys are thinking deeply. So how do you do debugging when you're, I guess this does depend on the speculative model. First of all, basically, debugging is in general tough when there's optimizations enabled, right? For example, when you want to debug your code and the compiler is doing some optimizations, usually you compile it in debug mode, right? And that gets rid of a lot of the optimizations. Because to be able to debug your code, the code that's being executed should really be the same as what you've written. Right? Otherwise, you have a lot of problems. So it's very difficult to debug optimized code, for example, something optimized by the compiler. So in this case, the hardware itself, let's take the case of multiscaler. So multiscaler itself should provide the guarantee of precise exceptions. Right? It may be underneath. So what happens underneath is not exposed to the programmer in multiscaler. Right? The programmer still sees a sequential execution model. But multiscaler underneath takes that code and executes it in parallel. So debugging should not be different from what you would normally do in a single-threaded processor with multiscaler. Right? Because what's exposed to the architecture, the architectural state that's exposed to the programmer is the same as the architectural state that would be exposed to the programmer if you were executing in a one Neumann machine. Right? That's the beauty of the precise exceptions. And multiscaler preserves that. And I believe a lot of the other models preserve that also. Actually, yes, Slipstream, for example, preserves that. Dual core execution preserves that. So debugging doesn't change in those models. But for the other speculative models, like speculative models with parallel programs, then that's a different issue, right? Then you have all the debugging issues related to parallel programs. OK? Let's see. I guess Mihir is asking a question, but I don't know if you can ask a question by using your phone.
We can enable his.
Yeah, let's try that. Last time we tried that, it didn't work.
His microphone is enabled.
OK.
A little bit of feedback. Do you want to try turning on your sound, Brian?
OK. You'd better type. Let's try it again. Why don't you speak?
Is that not working?
OK. It's an experiment. So hopefully we'll make it work someday.
He is audible, but there's
OK. I cannot hear anything. But OK. In the meantime, so basically, as long as the architectural model is preserved, the debugging should not change, right? Now, the debugging of the hardware itself is another issue. The hardware should execute the program correctly, right? In multiscaler, for example, multiscaler cannot speculatively parallelize and lead to wrong result. But that's another issue. Software programmers should not worry about that if the hardware is designed correctly, right? And the compiler is designed correctly. OK. OK, what else? I guess we'll get a question later on. But any other questions? Yes?
There's about this last point you just made with debugging hardware. Are these hardware designs formally verified usually? Because the complexity is enormous. To get it right seems to be impossible.
Yeah.
Are they verified?
So that's a great question. It's very tough to do formal verification. People try to do formal verification in small chunks of hardware.
Can you repeat the question?
But yeah, are the hardware designs usually formally verified? How do you do the verification of hardware's correctness, basically? People have done a lot of research on that. Actually, Edmund Clark, who's a professor here, has won the Turing Award in some of the research he's done in that area, basically hardware verification of hardware. It's tough because the designs are becoming much more complex, right? First of all, you need to formally specify what happens, and then verify it running a model checker, for example, whether the model, whether what you developed actually satisfies that model. And as complexity becomes larger, like with something like multiscaler, it becomes much more difficult. Usually people have looked at formally verifying simple pipelines. And you can do that with some ease, but even then the state space is very large, right? With microprogram designs, it's relatively easy to formally verify, right? Microprogramming, as we've discussed in 447. And if you don't know what it is, go back and look at 447. But basically, simpler designs are easier to verify. But usually, if you look at companies today, formal verification is done at smaller scale, at the component level. But it's very difficult to do it at the system level. Like doing it for a multi-core processor, or even a multi-thread processor is very difficult.
So what does Intel do? They just hope it's correct.
So there's a lot of testing that happens, certainly. There's a lot of, yeah, exactly. It's not hoping it's correct, but it's really, once you get the hardware, actually, even before you get the hardware, you do a lot of simulation with different kind of test vectors, and you try to figure out if the behavior that you expect with this program, with this functional program, is satisfied, for example. So there's functional testing that happens with different types of programs, and you look at whether the result is correct. That's one level. And that actually covers a lot of cases, a lot of bugs that may have been in the design. And then you go to the next level, because functional tests may not cover everything. You may have problems in the underlying design, right? Performance problems, or even other problems. Then you put you can do module level testing, right? You can have inputs and outputs, and you want to make sure that the outputs match the golden outputs for a given input. So that happens also. And then I guess you do have some formal verification at the component level also. So it's a bunch of different techniques. It's really a toolbox. Maybe we can have a lecture on verification too, related to that. But that's a big area as well. So some of the techniques that Yanjing will talk about will cover that. You can ask that question at that time also if you would like. But there's no perfect way of verifying today. Because if there was a perfect way, actually, you wouldn't see the errors, right? If you look at a microprocessor document, a hardware manual, you'll see errata. And these errata are things that are found after the processor is shipped. And they occur in rare conditions, but they escape because you cannot fully verify the design. Actually, it's interesting to look at some of those errata. I would encourage you to do so. Yes?
Because it's just somewhat bothersome that you can write a paper and then you write it in high-level C code, do all your simulations and prove it's the best idea ever, but then you sort of leave it up to the people who would be designing the hardware to actually see if it's even real to design, test it to a degree that's acceptable for the market.
That's right, exactly. So the question. So your question is, like, how is this a good approach to research, or
widely accepted to not argue in your paper that
Oh.
you're presenting something actually practically
I see.
implementable?
So that's a good question. Basically, the question is, why is it an acceptable paper if the paper doesn't address whether or not the approach is practically implementable or verifiable or in hardware? So I think that's a good question. That depends on what you want out of research paper. A paper cannot solve all the problems. It's very difficult to do that in a single paper. First of all, you have limited amount of space. But what you said is correct, actually. You really want to get the idea out, and with hopefully a very good, strong evaluation, right? But you cannot look at all of the possible aspects, like the verification aspects. But you can anticipate some of them. You can discuss potentially this could increase the verification cost, right? But it's very hard to evaluate because you don't have the full design also in a paper. So the task of a research paper in general is to come up with these ideas that can potentially improve the design. But usually it's left up to someone else who would like to take the idea, potentially, and implement. But basically, usually it's up to someone else to verify the idea. So the goal of the paper is to say, oh, this is a good direction to examine. And maybe in the next paper, you'll look at the verification issues related to the idea. For example, with multiscalar, it's very tough to, there are a lot of issues in the execution model to begin with, to solve. So before you get to verification, you should solve those issues first. And then maybe after some time, the idea becomes implementable. Does that make sense? Yeah. So data flow is another example. For example, a data flow execution model. You start with a high-level idea. Maybe the execution model should be this way, because you exploit much better irregular parallelism. And here are some initial ideas on how to design the architecture. And by the time you get to verification, you should solve all of these other issues that are related to data flow. Verification is an issue also in data flow models. Yes?
So companies like Intel, they just, when they see these ideas, they just build them on top of existing designs?
Mm-hmm.
Or is there a time where they decide, okay, we got to start over?
So that's a very good question also. Basically, the question is, when you see an idea in a research paper and when the company thinks that it's implementable, what do they do? Do they try to put the idea on their own current design? Do they try to stitch it there? Or do they start with a completely clean slate and redesign the microarchitecture, let's say? Intel usually keeps the ISA the same. But and I think that's a continuous discussion within those companies also. Basically, usually what happens is, it depends on the idea, first of all. If the idea is proposing, for example, something that can be easily adapted to an existing microarchitecture or existing architecture, then they can take that and adapt that to their own system. For example, if you're proposing a cache management policy that's much better in efficiently utilizing the cache, it's much easier for a company to take that idea and use that, right? Does that make sense? But if you're proposing an execution model that's totally different and multiscalar, then the question is, like, what are the maybe there are sub-issues that people working on a product find similar in their design to the multiscalar design. For example, memory dependence prediction that we discussed last time. People who are working at Intel or some other company found that this memory dependence prediction problem also happens in out-of-order processors, and they can use potentially some of the ideas that are published in past papers. Right? So it depends on the level. Now, when do you rethink whether you should go to a new architecture? Well, that's a decision that's made based on many factors, right? So, for example, Intel had different architectures. They started with many processors, but they had the 486 architecture a long time ago, 8486. Has anybody used those? You guys are too young then. I think one of my first computers was a 286, 8286. Then 386 was after that, 486 is after that. These are basically in-order, simple in-order pipelines, very simple machines. And then Pentium came along. It was an in-order superscalar pipeline, actually Pentium 2. And then a Pentium Pro came along, which is an out-of-order. So that was a complete redesign. So between Pentium 2 and Pentium 3, you have a complete redesign, which is going from in-order superscalar to out-of-order superscalar. Now, how did they make that choice? Well, they wanted to scale the performance, right? Because it was there was a lot of competition from RISC companies, for example, reduced instruction set computer companies, where it was easier for them to get performance because the compiler could reorder the instructions. So Intel was looking for a way to actually get higher performance by tolerating longer latencies. And out-of-order execution was one good way. So they redesigned the entire architecture to implement out-of-order execution. So it really depends on the benefit of the idea. Out-of-order execution provide a lot of benefits according to their simulations. And also, like, I guess what happens to the competition? These are factors that are not necessarily technical, right? If you have no competition, it may be easy to just keep churning, adding more stuff to your existing microarchitecture. But at some point, that also becomes difficult to verify, right? If you keep adding stuff to your microarchitecture. So I don't have a perfect answer to that question because it's a mix and match. If a company sees an opportunity, I think, in industry to actually adopt a totally different execution model, they may try to do so. But it's a lot more risky, of course. Does that answer kind of your question? But as a researcher, on the other hand, it's always good to look at both types of ideas, right? Research is, in a sense, more opportunistic in that sense. Richard Feynman once said, the best ideas, the best problems are problems where you have ideas to solve. Right? There's no small problem or big problem. If you have an idea to solve a problem, that's a good problem. You guys know about Richard Feynman, right? Yeah. Okay. Okay, is there a question here?
Yeah, I guess going back to the debugging.
Yeah, suppose if the programmer puts breakpoints on memory access, then the programmer comes to know of the event much after the actual occurrence of the event. Well, so that doesn't, I guess that's a good question. Let me think in what context this will happen. I guess it depends on what context this happens, right? If you're doing multiscalar, for example, the illusion is that the stores are committed, or the memory operations happen, at least architecturally, at the time they appear in the sequential code. So this is not a problem, right? Architecturally, the programmer sees the operations in the sequential order it writes, because multiscalar preserves a von Neumann model. So this should not happen in any speculative execution model that preserves the von Neumann model architecturally. Right? Now, this could happen in transactional memory, but because it doesn't preserve the von Neumann model, right? Because it's a parallel program by definition. Right? It's not a single-threaded execution. Okay? Yeah, the key is preserving that semantics such that the programmer knows that at that breakpoint, all of the operations that come before the breakpoint are committed, and none of the operations that come after the breakpoint are started. That's the von Neumann model, right? Sequential execution. Okay, yes?
So when we write a paper or do the projects, maybe we design some supplementary hardware to help implement our policy or strategy. So how to model those supplementary hardware, like a memory controller, a memory controller utilizing very complex strategy.
Mm-hmm.
So how to model them? So we generally estimate the latency and energy cost and put those numbers in the simulator, or.
Mm-hmm. I see. So let's say you have this additional piece of hardware that you want to add. Let's say a new memory scheduling policy. Okay. Let's pick a concrete example. You're asking, how do you model the latency?
Yeah, how to model that.
Like how long it will take?
Yeah.
So a good way when you're doing architectural simulation, if you have an idea to explore, is to start at a higher level and model it at the algorithmic level. Model the operation of the memory scheduler and vary the latencies.
Oh, vary the latency.
Yeah, because you may not know what the latency is, and you don't want to, before testing the benefit of the idea, you don't want to design the hardware. This is one particular kind of research that we're talking about. Let's say you come up with a great new memory scheduling policy that you think it'll work. Maybe, for example, a reinforcement learning memory controller. A memory controller that operates based on reinforcement learning principles. And I'll recommend a paper. Actually, you read that paper, right? Oh, we haven't covered the memory hierarchy lecture. So you will see that paper. but I'll point you to it right now. Well, this should be one of your readings. I'm surprised my web page is not here. Yeah. This paper, for example, in this paper we had proposed a memory controller that adapts its policy dynamically using reinforcement learning. It's really a reinforcement learning agent. I'll show you one example. And I'm showing you this example because it's a relatively complex memory controller. So how does reinforcement learning work? Basically, you have an agent, learning agent, that observes the state of its environment. It could be how many transactions you have in your transaction queue in the memory controller, for example. What are the properties of that? So you can have a bunch of different state properties. Based on that state, it takes an action, basically scheduling command, next command. That's the action. And then based on that, it gets a reward from the environment. This is general reinforcement learning. And reward can be basically something that the agent is trying to optimize. Right? It gets a positive reward if it does the right thing to optimize that. So memory controller can be modeled this way. That was the realization in this paper. We basically have a memory scheduler that can look at its transaction queue, the state attributes, and schedules a command. And based on that scheduling, it gets a reward. And the reward could be data bus utilization. Is the data bus utilized or not? Right? Not all commands lead to data bus utilization. For example, only read or write leads to data bus utilization immediately. Right? If you do an activate, you don't utilize the data bus with that command because you're bringing the row into the row buffer. So you'll see this in more detail in one of the lectures. But that's the basic idea. So this memory controller actually can be complicated because it needs to have a table that maps these state attributes to a scheduled command. This is called the state action pair. Right? For any given time, when you want to schedule a command, you basically have a bunch of different, you have a state at that point, and you have a bunch of different actions that you can take in that state. And each of them have some value. So you associate a value with each of them. At this state, if I take this action, I'll get this kind of reward into the future. And you learn this over time. And your goal is to maximize the reward. Pick the state action pair that actually maximizes that value. I'd encourage you to read the paper. Actually, if you're taking the machine learning course and if you learned about reinforcement learning, a lot of reinforcement learning mechanisms work this way. But basically, you need that table. And there are a lot of trade-offs associated with that table that you can read about in the paper. And I think in this paper, the table is about 32 kilobytes. Let me try to reduce this. I guess I don't know how to go down. Yeah, you can see the algorithm over here. I guess then the key question is basically, actually ignore this for now. How do you evaluate something like this? You certainly implement the algorithm in your simulator. Instead of using FRF-CFS, for example, or hit first scheduler, you basically implement this algorithm. And you can read it on your own. Basically, for a DRAM cycle, you issue a command, you look at the reward, and then you look at possible commands you issue. And ignore this for now. We may get back to it. But basically, this is the tough part. Select the command with maximum Q value. This is what we talked about. Select the command with the maximum possible reward into the future. Right? That would maximize your reward into the future. So this could be tough, actually. It's nice. It's a nice function call. It's actually what you would write in your simulator also. But in hardware implementation, this is a hardware implementation because you need to query a table with different actions that are possible for this state and get different Q values and compare those possible rewards, find the maximum. Right? Does that make sense? That's how you would maximize the reward. Then the key question is, how long does it take, for example? That's your question, right? How do you model the latency of this? Well, what I would suggest in this case is initially to assume no latency. What if you don't have any latency to do this? What if the latency is the same as the baseline? Then you get a performance result. And then you vary that latency from 2 cycles, 5 cycles, 8 cycles. And then you get different performance results. That's usually a good way when you're doing performance studies. Varying the latency, if you do not know what the latency of the parameter is. And then the next step, which we did in this paper, is actually think about a hardware implementation and justify a potential latency. Right? So if you go through here, go through this paper, I believe I've assigned this as a required reading. Can someone verify that? It is? Yeah, in the next 2 weeks. So you're going to be familiar with this paper. But basically, this has a sketch of the hardware implementation of how this could work. Right? And these are the pipeline stages. So it takes about 5 cycles to make this decision in the memory controller. And since you're going to read this paper, I'm not going to go into detail on how this works. But a good paper goes into that detail implementation also, if it's not intuitive how to implement a new algorithm like this. Does that answer your question? Yeah.
So it's like we start with no hardware cost
That's right.
or latency cost, and then vary the parameter to see
That's right.
performance.
That's right.
And then we give a very detailed implementation plan.
That's right.
Estimated the area or something.
That's right. Yeah. So here we stopped here. Basically, we estimated the area using some tools, but we didn't go and implement this in RTL. That could be the next step, right? That could be the next level in research. Well, we stopped here at that point. Yes?
Yeah, can we do that like a pure mathematical way, like just see how the time complexity of each operation and stuff like that?
If you can do it convincingly, yes. So it's a matter of how convincing you could be in a pure mathematical way. If you do not do this kind of design, I think it's going to be tough for this particular problem. But for other problems, it could be possible. I'll have to think about the specific problem. Yes?
The student wants to know if load balancing techniques will be discussed in detail following lectures, or things with optimizations like ACS. How is load estimation done?
OK. So load balancing techniques, we discussed them in a previous lecture, right? Parallel task scheduling, for example, we briefly discussed them. I'm not planning on going into more depth, but I encourage you to send me email about potential papers, like what you have in mind. Shiva, right? Yeah. But the specific question, how is load estimation on each processor done with ACS, accelerated critical sections? So accelerated critical sections doesn't really do any load balancing, right? Whenever you get to a critical section, ship it to the large core. So in that case, there's no provisioning for load balancing. Except for the case, I guess, one load balancing that happens is to prevent the false serialization, if you remember. If you actually have different critical sections that are waiting to execute in the large core, and if this is happening a lot, ACS has a mechanism to kick out a critical section and say to the small core, don't send me this critical section anymore, right? To reduce that false serialization. So that kind of tries to balance the load on the large core, right? You could think of it that way. But other than that, there is no explicit mechanism to do load balancing across cores. You could potentially think of distributing the task of, we discussed this a little bit in one of the earlier lectures, distributing the task of handling critical sections to different processors, right? So if you have multiple cores, for example, multiple large cores, now you may want to balance the load of critical sections across those 2 different cores. And one way to do that could be, for example, based on the lock address, you can hash the lock address and pick the core based on a hash function on the lock address. And those locks go to this, those locks that map to the same core are executed on that core, are shipped to that core. And then your load balancing is as good as your hash function, as good as the load balance your hash function provides. OK? OK. But going back to your question on if you actually devise an architectural optimization, it's always good to vary the latencies. It's always good to look at the sensitivity. For example, another paper that we will discuss, and I'll show you an example of this. And I don't like Chrome, I guess. That's what I decided. Problem is, it's another paper I would encourage you to read. Oh, I like this because I can open it separately. It's about compression, basically. If you, you have a compression algorithm, and well, why do you want compression? You'll see that in the lectures where we talk about caches. Basically, you have limited amount of space, memory space, and you would like to utilize it very efficiently, right? In this case, it's cache space. If you have redundant data, why don't we compress it in cache such that the same amount of cache appears as if it's really a larger cache. It can store more information in it. And the idea Gennady had in this paper was a lot of the values stored in cache lines. I guess I'll give you the idea before I make my point. Look like this. It's always, when you write a paper, it's always good to have one figure like this. When I look at it, I say, aha, I'm done. I know the idea, right? Let's strive for that. That's a really good thing. So this figure is kind of like that, I think, in my opinion. Let's see if I can balance it. Can you guys see that? Yeah. Basically, this is one cache line example from a real workload H.264 encoder, video encoder. And cache line looks like this. It's a 32-byte cache line, cache block. Basically, it consists of a lot of narrow values. It has 8 4-byte values, and those 4-byte values are very close to 0, if you look at this. So there's a lot of redundancy in this encoding, right? You don't want to store all of these zeros. So the key idea is, why don't we have a base, a common base, and encode all of these different values as small deltas from that base? And these are the deltas. If you do that, you can have a 4-byte base and 1-byte deltas and encode these without any loss in information. And you save basically 20 bytes. So that's the idea here. And there's another example here with pointers, right? It doesn't have to be all close to zeros, but sometimes you have an array of pointers, and the pointers are very similar to each other because they come from a similar memory space. So you can encode that by having the first element as the base, and by encoding all of the elements as deltas from that base. In this case, you save, I guess, luckily 20 bytes again. So if I have to take one issue with this figure over here, I would say the scale is not right. This is 32 bytes, and this is 20 bytes, right? But that's OK. That's to save space in the paper. Or actually, it's not scaled well. OK. But that's the idea here. So then the key question is, how long does it take to do this encoding, right? Because when you bring the cache line from memory, assuming that memory is not compressed, basically the cache line looks like this. And when you are putting that into the cache, you'd like to have a compressor that compresses into this, right? And that compressor actually is not that simple. Well, I'm hoping, yeah, that's the decompressor. And there should be a compressor somewhere. Yeah, this is an example of a compressor, I think. Yeah, actually, this is the compressor. If you read this paper, this is kind of the compressor. You get a 32-byte uncompressed cache line. There may be many different ways to compress it, right? You can have an 8-byte base and 1-byte delta. You can have an 8-byte base and 2-byte deltas. And you can have a 2-byte base and 1-byte deltas. So those all can give you compressed cache lines. Or you could figure out the entire cache line is zeros. In that case, you don't even need to encode it, right? You can have just 1 bit in the tag store saying that this is all zeros. Whenever you access it, just get zeros, right? And then there's a replicated value compression unit. So you look at this, and each of these compressors can decide whether or not the cache line is compressible this way, and there's a selection logic that provides a compressed cache line in the end. Then the key question is, how long does this take? Right. Well, a good way of, a good architect would do, I think, is basically vary this latency. Right? Say, I'm going to assume, I'm going to evaluate this, and maybe evaluate 1 cycle, 5 cycle, 10 cycle latency. Right? And then look at the performance result. Because otherwise, you'll need to design this entire thing to figure out the latency, right? But right now, you're at the stage of evaluating the idea. Does this even make sense to improve performance? So it's better to do that first. And then if you see, then you'll see a knee of the curve, right? Actually, it's not in this paper, but this study was done by Gennady. Usually, what happens is compression latency is not on the critical path, right? Because you're getting the data from memory, and you can directly supply it to processor, right, while it's being compressed. So the processor can continue with the data that it needs. But decompression latency is usually on the critical path. So you have a compressed cache. You hit in the cache, and you want to access the data. Then you need to decompress. Right? So that turns out to be on the critical path, because you cannot directly supply the data to the processor because it's compressed. Right? So that latency is a lot more important. And that's one of the benefits of this compression mechanism. Decompression is relatively fast. So if you look at this, yeah, well, that's the compressor unit, sorry. Yeah, this is the decompressor unit. Basically, you access a compressed cache line, which consists of base and deltas. And decompression unit basically is a vector addition engine, right? In parallel, you add the base to the different deltas, and you reconstruct the uncompressed cache line. So then the key question is, how long does this take, right? Well, it takes as long as an addition, a vector addition takes. Now you can again vary that latency, right? 1 cycle, 2 cycle, 5 cycles, and the paper has that somewhere. Does that make sense?
So in this case, we kind of estimated the latency of the common adder, and you use that latency as a.
Yes, exactly. You could do that. In this case, you can actually estimate the latency of an adder. But again, it's still good to vary the latency, because your adder may take 1 cycle, but someone else's adder may take 5 cycles, right? So it's always good to do these sensitivity studies in your paper, or whenever you propose an idea, because you'd like to determine the conditions under which the idea works or doesn't work. OK? OK, that was a long-winded answer to your question. But these are actually good ways of having your research reach bigger impact. If you assume a single latency, then, or if you assume a single workload, then you're limited to that workload and latency. And someone else has to evaluate that for themselves. But it's always the case that someone else needs to evaluate this idea. For example, this idea, actually, it's been evaluated by companies after it was published. But they cannot just take your results and implement and put it in the next processor, right? That just doesn't work. They need to actually evaluate in their design, right? They need to take the idea, implement in their cache, and see what is the benefit in their cache, in the system they're designing. But the more information you provide in your research project, the more likely that people will evaluate these designs. Or you can start up your own company and design your own processor, which I would encourage you to think about also, if you have good ideas. OK, what else? That's been a good discussion. Yes?
On cache coherence,
Mhm.
so the token coherence paper mentioned that they compared against some other closed source hammer algorithm that was
OK.
proposed as also being in between the broadcast based and the directory based.
Uh-huh.
So I was just wondering if since then if there's more details released about this magic other algorithm.
Did they cite any paper related to that? I don't remember actually.
An industry like from AMT.
Oh, this is AMD's hammer algorithm. So that's a good question. I haven't kept up with that. So the question is, yeah, in the token coherence paper, if you look at it, there's a comparison to AMD's hammer algorithm, right? And it's closed source, and the paper doesn't describe it, right? The citation is to an industry, something technical report, and not even a white paper maybe, that doesn't talk about it. The question is, were there any details released about this algorithm since then, since the publication of token coherence, which was at Micro 2003, right? A long time ago. So the answer is I don't know, actually, because I haven't kept up with that. But maybe anybody else know how that works? You worked at AMD, maybe you know. But maybe you could. Oh, Moesi?
Yeah.
Okay.
Just a regular SEO.
Okay. But there's no optimization?
Just minor ones, nothing.
Okay. Okay. So yeah, one source here. But yeah, as far as I know, there are no publications. Are there publications related to that? Okay. No. So Moesi is, we covered this in coherence lecture, so everybody knows Moesi, hopefully. It's a 5-state coherence protocol. So you'll be ready to answer what that owner state is useful for. I'll not repeat it right now, but you can. So be very comfortable with MSI. What does the additional E state provides you in MESI? And what does the additional O state provides you going from MESI to Moesi? That sounds like a perfect exam question. Maybe not in that way, but. These are actually good interview questions also if you want to get a job in some company. It's good to know these. Guess what else? I was going to talk about memory a little bit more, but we don't have a whole lot of time. But if I'm happy to continue answering questions and defer the memory scaling discussion to either Friday or next Wednesday. Yes?
I have a question about consistency models.
Mm-hmm.
We only did sequential consistency. Are we going to get into relaxed consistency and the other weaker consistency model? Which is one that's actually used these days?
That's right, yeah. A lot of the models today use some sort of relaxed consistency, like total store ordering. So they don't have a total or the sequential consistency is very strict, right, as we discussed in lecture. We've covered briefly, and I've given you pointers, but I don't intend to cover those models in detail. But we can do some reading if you want. I'd be happy to talk separately. But yeah, it is true today that a lot of the consistency models that are used, actually it's a mess. That area is kind of like a mess in architecture. Actually, it's not in architecture only, it's in distributed systems too. Like how many times have you opened Google Gmail in multiple different windows and figured out that the message you've deleted in this window is still over there in the other window, right? That's a consistency problem, right? Because you have multiple copies of the data, and actually the updates are not consistent. I think it's a distributed system. And I think some of the guarantees that are provided today in those distributed systems there's this notion of eventual consistency, which basically says eventually you will get the right data. But that eventual is never specified strongly. So you see that this is an issue actually in multiprocessor systems as well as distributed systems. But if you look at a processor, a multiprocessor, sequential consistency has not been implemented because it has costs, right? You need to ensure that the ordering appears the same to all processors. And that requires a lot of snooping, for example. So a lot of the models are more relaxed consistency today. Like you do total store ordering, which is essentially at some level you ensure ordering of stores, global ordering of stores. But there are some other small other things that I don't want to really get into right now because it's a complicated concept. But if you're interested in this, I can recommend you some papers, and maybe we can talk about it some other time. Maybe I already did recommend you these papers. Let's see. Did we talk about this? In the lecture, I think we did talk about it, but yeah, this paper, memory consistency and event ordering in scalable shared memory multiprocessors. That paper introduced the release consistency model, which is actually maybe I'll take.
It's mentioned in module 2.3.
Yes, okay, thanks. Yeah, I did not assign this, but I would, if you're interested in this area, I would recommend you to take a look at this first. Yeah. Yeah, basically, it's really trying to ensure ordering between acquires and releases. Right? Acquires, release, acquire, release, acquire, release. You have that ordering across those operations. But these need to be marked by the programmer. But this is something I would recommend you to take a look at, and then we can talk. Okay. So a lot of the topics actually that we cover, I give you like the basics, and we don't go into a whole lot of detail after that. There's a lot of research that has happened in consistency and different consistency models too. That's true for caches also. I will not be able to cover every research in caches, but I'd be happy to recommend you papers. And this is something I would definitely recommend you to look at. Unfortunately, there's no great tutorial, I would say, on consistency models. This is an area that's lacking. If you're excited about this area, I would maybe you can be the leader and you can actually describe and categorize these different consistency models. Different processors implement different kind of consistency models, and sometimes it's hard to reason about them.
But this is sort of exposed to the programmer.
That's right. This is exposed to the programmer.
There's no standard about this? Because
Yeah, there's no standard actually. If you sometimes even the compilers do optimizations that violate the consistency that the programmer would expect. There's a good paper on that actually. It's a little bit tough to read.
so then if you can't run the same program on different systems with different models and expect it to work.
That's right, exactly. People have done those experiments. You run a well-synchronized program that runs nicely on one system, and then you move it to another system that has a different consistency model, and you may get the wrong result. I say you may get the wrong result because this all depends on the ordering of the events, right? That's why sequential consistency is nice because the programmer can easily reason about that, right? If everybody implemented some sequential consistency, then the world would be almost perfect, right? But we've discussed some potential implementation issues with sequential consistency, right? The other paper I would recommend is actually the papers that try to implement sequential consistency in simpler ways. And I think that's a nice direction because it's a clean direction. This was part of Louis Cézé's thesis at Illinois, so I would recommend that. It's in ISCA 2007. Bulk SC, bulk enforcement of sequential consistency. Oh, I guess there is no website with that name, huh? Yeah, I don't know if there is a single figure that gives me the idea here, but yeah, basically the idea is actually relatively simple. You don't enforce sequential consistency at each individual load store level, but you look at a bulk execution, chunk execution of programs. You chunk the program into instructions that are on the order of like maybe 1,000 instructions. And you ensure consistency across those chunks to increase the granularity at which you ensure the consistency of memory operations. This reduces the amount of state you need to keep track of. Right? So I'd encourage you to take a look at this. If you don't understand this right now, take a look at the paper. in general, if you look at operations at a coarser granularity, you can reduce the overhead if you can do that. Because all you need over here is to ensure that the interleaving is correct, right? Access interleaving that all processors see is the same access interleaving between loads and stores. It doesn't matter if you do it at the individual load store level or at the chunk level. The observation here is that by doing this at the chunk level, you can actually implement sequential consistency much more easily in hardware. And let me see if there's a figure over here. I guess there's not, but I'll let you read it. Does that make sense? At some level?
So it just talks about implementing sequential.
That's right, yes. Yeah. But the idea is doing it at the chunk level, right? Like coarser grain instruction level, at the bulk level, as they say. But this is another direction, basically. This is like how do you get a good consistency model? Because sequential consistency is very nice for the programmer. The programmer doesn't need to worry about. So with the relaxed consistency models, the programmer needs to put fences, for example, right? Memory fences to ensure that all of the operations before the fence has finished and nothing has started. That enables a global ordering of operations at fence. And if the programmer forgets a fence, your memory, your program can be incorrect, because you may be actually doing an operation that modifies a shared variable, right, before the fence. Or you can get different orderings and different processors, right? Whereas with sequential consistency, the hardware guarantees that every processor sees the same order of operations. So it's a lot nicer, in my opinion, to keep that model that makes life easier for the programmer, but figure out how to implement in a simple way. That's why I like the approach of this paper. Release consistency model was proposed at that time to basically be able to scale, to be able to implement a lot of the optimization techniques, memory optimization, caching, out-of-order execution, prefetching, while preserving some nice properties for the programmer. But it still requires programmer to insert fences.
Is this like a mode you can change in processors? They
Oh.
implement more than one?
More than one consistency model? Implementing even one consistency model is hard. Implementing even one consistency model correctly is hard. So I don't think there are any processors that can change that. I guess you could relax it easily, but then you need to ensure that the relaxed model obeys some requirements that the programmer can reason about. Right? So that adds additional complexity. Are there processors that have different modes? Not as far as I know. But there's another paper that I'm thinking of that demonstrated the incorrectness of programs when you move from one processor to another processor. If you remind me later, I'll tell you about it in the next discussion. Or at least I'll point you to it. Okay. What else? This is a good discussion. We've been talking about a lot of different topics. So if there's anything in your head about the lectures, feel free to ask now. I guess to jog your memory, we've covered a bunch of lectures. Oh, great, Brian is handling some of the questions that's happening over there. Not this. Yeah, we've had a bunch of speculation lectures. Cache coherence, processor consistency. So feel free to ask. If you don't ask, I think we'll probably end the lecture. Or ask anything, like project questions also. I don't want to start on memory scaling right now. Yes?
In speculative law collision, the paper talks about how you use cache coherence to keep track of when another thread is accessing data. So what do you do if you have multiple threads in sharing a cache?
if you have multiple threads sharing a cache, I guess the question is, I see. Basically, in speculative lock collision, you would like to detect a conflict that happens between two threads. If one thread is in lock collision mode, it should basically monitor the coherence requests that come from other threads. If it's seen an invalidation request to a line that is read or it's trying to read them, it basically aborts, right? That's what happens in this case. So if you have two threads sharing a cache, you won't see that invalidation request, right? For example, in an SMT processor, if you're doing speculative lock collision. Well, in that case, you will need to change the cache, I would argue. Speculative lock collision did not talk about that particular case. But in that case, you will need to detect the conflict between those two threads. And there's no way to detect it if this thread is actually writing to this block, and this other thread is going to read from that block. So you will need to have the bits saying some other thread wrote to this block, and this thread is going to read from that block. Does that make sense?
Would that work? Wouldn't that get really messy?
So basically, it's like read-write bits per thread, per hardware context. So speculative lock collision, I guess, do they use read-write bits? I don't remember the paper itself. They don't use read-write bits, right? Some other approaches to transactional memory actually add bits to each cache line saying this was speculative read or speculative written. 1 bit per hardware context. So you will need to do the same thing in that case.
Maybe you could make it atomic for that one code. That section could be atomic for that one code. So
Mhm.
threads can't access that critical section in the same code.
I see. Yeah, I guess since the core is so tightly coupled, you could potentially, that could be another solution, right? Now we're trying to solve the problem. That could be another solution, that's right. If one thread reaches a lock that's going to elide, it can basically record it somewhere saying that, oh, I'm eliding this lock. Another thread that's executing on the same core maybe cannot enter that. Maybe it waits. Now that reduces parallelism. That's the downside of that solution. Because maybe there's going to be no conflict between those threads, right?
Yeah, that becomes more like transactional memory where you state.
Now I think the solution is, in this case, you don't even enter that. So it's different from transactional memory. If you detect, because the two threads are executing on the same core, it's an SMT, multi-thread processor. If you know that one thread is acquired a lock in a speculative way, it's eliding the lock. It records the lock address. And if the other thread is going to elide the lock also, it won't elide the lock until this thread gets out of that critical section. So it's basically serializing for that particular critical section. That is a solution that would get rid of the additional bits. Because the additional bits are needed if the threads are executing on the same core, sharing the cache, right? But that would reduce parallelism. What else? Do you have more questions? It's good to ask. This is exactly what the discussion is for, actually. And if you ask, it helps others also. But this is kind of what I wanted to cover, actually. But I don't really have time to cover all of it, so I'll try to do it either on Friday or next Wednesday. What do you guys prefer, Friday or next Wednesday? Who says Friday? Some people. Don't be shy. Who says next Wednesday? So I guess more people say next Wednesday. So one discussion per week is usually enough, you guys think? OK. The downside is there are some people who can make the Friday, some people who cannot make the Wednesday. So do you prefer an in-person discussion of this, or do you prefer me to record this? In-person? In-person, at least for people who are in Pittsburgh, obviously. Unless you guys want to fly out from other places. Who prefers online? Okay. Okay, maybe we'll do this in person next time. But basically, I'll give you an overview. Since we're starting the memory hierarchy lectures, I'll give you an overview of the state of the memory system. And this is a relatively short, like a 1 hour talk that talks about some of the issues, which is kind of based on the memory scaling paper you read, but you'll see it live. Actually, a lot of the topics that I'll discuss will be covered in lectures in more depth. But basically, I'll talk about this. And I think this is something good to ponder about. I see three key problems in system design today, in architecture design. One is the memory system, or data. Basically, data storage and movement limit performance and efficiency today, much, much more so than it used to in the past, because we have all these data-intensive applications. We're putting multiple cores, multiple agents on the same chip. And this will become a much bigger problem in the future, and it's already a big problem, the memory system. So that's what we'll focus on. But I think there are two other key big issues in systems today. One is efficiency, obviously. I don't think these are controversial at all, actually. But energy efficiency is very important, because this really limits your performance as well as scalability in every system today, almost. And the last one is predictability and robustness. And we'll have a guest lecture in terms of robustness, in terms of resiliency, reliability, as I discussed on October 21st. But reliability issues lead to predictability issues also. But there are other predictability issues. Predictability issues arise from unreliable, unavailable hardware. Actually, you're noticing that perhaps with the US government these days, right? There's a big availability problem that we have in these days. Is that right? When I go to some websites, for example, they say, what was the phrase? Due to lack of funding, or no, due to a lapse in funding, this website will not be updated or will be unavailable. So that's an availability problem, right? And you don't want that in systems. You certainly don't want it in the government. But basically, this predictability and robustness is a key problem in systems. And we'll talk about that from both the robustness perspective as well as quality of service perspective. So these have become first-class constraints as systems scale in size and technology. So in this, I guess when we talk next in Wednesday, we'll talk mainly about the memory system. But we will talk about this in later lectures. And a lot of the lectures have this theme of efficiency, if you will. So these are really good problems to actually research going forward in systems and architecture. OK, but our focus will be on memory system. And we'll do it on Wednesday as you guys wanted it. Okay. Anything else before we part? OK, I guess I'll see you Wednesday.